I'm calling this video the rest of kinetic energy, the parts that are often ignored. Usually they don't even come into play, but in some cases they do, and those cases are called reality. Scientists have several conservation laws. One is the conservation of energy, but to use it, one must consider all forms of energy. We do not have a conservation law of kinetic energy. It's okay for energy to be converted from one form to the other. Kinetic energy is energy of motion. So let's understand kinetic energy with an example. A sphere and a cylinder with identical masses and radii, both at the edge of a platform at a height h above the ground. They are at the top of the same ramp. If they are both slightly nudged, discuss the energy they each have at the bottom of the ramp. Will they be moving at the same speed, or will one be going faster? Assume their surfaces are the same material, so friction will convert their energies equal amounts of heat energy. So here's the ramp. The area in here, there's a height that things have to go down and be about here at the back of the ramp. This is the sphere, this is the cylinder, poised to roll and facing toward you. First, both objects produce heat energy due to the friction. Since friction is equal because they are of the same mass and they have the same material on their surface, they should produce the same amount of heat energy. While one object has a greater amount contact with the ramp, this also distributes the weight, so friction is the same for both objects. Heat energy is kinetic energy of individual molecules. This is impossible to measure since molecules are exchanging kinetic energy through collisions and at a pretty rapid pace. By the time you measure one, it has already bumped into some other molecule and exchanged energy. So what has to be done is a statistical approach. When we are told heat is a different kind of energy, that is not a good way of describing heat energy. It is really kinetic energy. It's just that we measure it differently. Another consideration is kinetic energy is energy of motion. Kinetic energy equals 1/2 mv squared. It's too simple for this problem. The objects will roll, and certainly an object rolling has energy of motion associated with that rolling action. Think about the Earth. The Earth spins on its axis. Would you say that spinning action had no energy associated with it? Of course not. There's energy in motion. Whether it's going forward or spinning, motion is kinetic energy. So the kinetic energy of rotation is given by the kinetic energy of rotation is 1/2 the moment of inertia times the angular velocity squared, where the moment of inertia, I stands for the moment of inertia, and omega is the symbol for angular velocity. The moment of inertia for a solid sphere is 2/5 mr squared. The moment of inertia of a cylinder is 1/2 mr squared. The moment of inertia of a point mass is I equals mr squared. So if we look at, say, a molecule orbiting around something, or even out a distance or from whatever it's moving about, the moment of inertia is mr squared. Moments of inertia of all the point masses of molecules must be summed. So what's happened is they've gone through, and it's a technique in calculus where you would find the distribution of the molecules in different shapes, and you would calculate the moment of inertia for that shape. So the moment of inertia of a sphere or cylinder is the sum of all the moments of inertia of the molecules distributed in them. The kinetic energy at the bottom of the ramp, the object, is the kinetic energy of translation, 1/2 mv squared, plus the kinetic energy of rotation, the term that sometimes isn't there. Of course, if the object's not rotating, it doesn't have to be there. 1/2 I omega squared. With V, the tangential velocity equal R omega. So that's how you translate from the rotating system to the translational system. The instantaneous velocity of something rotated with an angular velocity omega, a distance r out, is the tangential velocity v at that instant. So for the sphere, the kinetic energy is 1/2 mv squared plus 1/2 I omega squared, which is 1/2 mv squared plus 1/2 2/5 mv squared, mr squared omega squared. And for the cylinder, it's 1/2 mv squared plus 1/2 I omega squared is 1/2 mv squared plus 1/2 times 1/2 mv squared omega squared. Substituting with the v equals r omega equation, tangential, and translating the rotating r squared omega squared into velocity, we get tangential velocity. We get kinetic energy is 1/2 mv squared plus 1/2 I omega squared equals 1/2 mv squared plus, no, it equals, substituting v squared for the omega squared, r squared omega squared, we get 7/10 mv squared. So for the cylinder, we do the same, and we have a different moment of inertia, so we end up with 3/4 mv squared. The sphere will be moving slightly faster, since more energy is going into rotating the cylinder than into rotating the sphere. 7/10 is less than 3/4, so when we have the total kinetic energy of 3/4 for the cylinder, 7/10 for the sphere's got to be rotating faster since both will have the same kinetic energy at the bottom. So we'd have to have a higher rate of velocity. That's the only thing else that would change. So let's notice that when rolling things, well, not just falling, the idea that things fall at the same rate does not extend when something is rolling.